Hello everyone, in this video we are going to look at the basic concepts behind neural networks. Specifically, we'll look the representation of neural networks in a computational graph, and we'll look at how to represent linear regression models as neural network models, and lastly we'll consider the most important parts that is inside this neural network models, which is called nonlinearity. So let's start from that of the computational graph representation of neural network models. Now, neural network models are actually inspired by the biological architecture of the human brain, which consists of a series of interconnected nodes and information flows from one node to the other. So with this in mind, for example, let's consider the systematic component of any generalized linear model, which is the linear predictor or linear combination of the covariates. So Z equals B plus W1 x1 plus W2 x2 plus WP xp is the linear predictor of any generalized linear model, linear regression, logistic regression, Poisson regression, or any parametric survival models. So as it is, for example, we can consider this as a linear regression model. Z can be considered as an output variable or a dependent variable, or results of an outcome variable. Therefore, this can be written in this form in terms of computational graph. So here, for example, let's consider this representation, and particularly here we have this part is called an input layer and this part is called an output layer. Now the input layer consists of input nodes. For example, the input for this P, which is called intercept in statistical models, or which is called bias in machine learning. The input is 1, which is a constant term. And for the first covariate x1, we have a weight W1. And for the second covariate x2, we have the weight W2. And similarly for the P's covariate xp, we have the weight xp. So here W1, W2, WP are parameters or coefficients in the usual statistical models, but in machine learning we call them as weights. So here the inputs are here 1, x1, x2, xp, 1, x1, x2 up to xp. So here the input layer consists of p plus 1 input nodes. We call each input as a node, represented by the circle. So the input layer has p plus 1 nodes, specifically input nodes. And on the output layer we have only one node, and this node represents Z. Then here is just the output layer consisting of only a single output node, that is Z. So this is just a representation of multiple linear regression as a single layer neural network model. We have an input layer, we have an output layer. In fact, we have two layers. But in calling this neural network model as a neural network model, we do not call the input layer as a layer. Simply we call this as single layer neural network model. Single layer neural network model, provided that the input layer is also a layer, but it is not counted in expressing the neural network model. So this is the representation of a multiple linear regression model as a single layer neural network model. In the case of a logistic regression model, this linear predictor should pass through that of a logistic function or a sigmoid function in order to convert this value into a value between 0 and 1 inclusive, or in order to convert this value into a probability value. Then the architecture of the neural network representation for logistic regression is almost the same with that of this representation of linear regression. So the only difference will be on the output node. Here the output node will have a sigmoid function or a logistic function that transforms z into a value between 0 and 1. So here again we have an input layer and we have an output layer. Therefore this is just a representation of a multiple logistic regression model as a single layer neural network model. Single layer neural network model. So in the computational graph, a node produces an output that is going to be transmitted through an arrow, and the output of the node is multiplied by the weight assigned to that row or the weight assigned to that node, and then the product is going to conveyed to the subsequent node. Then all the inputs directed to the following node are combined through addition. That is, here we have this p plus 1 input nodes, and the weights of each node are assigned on their corresponding rows. So each input node, or the value assigned to each input node, is multiplied by the corresponding weights. 1 times b, x1 times w1, x2 times w2, and xp times wp. Then these products point to the following node here, which is, let's say, sigma of z. Then the products are going to be added, and finally here sigma of z is nothing but sigma of b plus the sum of wj xj. J runs from 1 up to p. So z is replaced by this linear combination. So a node just produces a certain output, and the output is multiplied by the corresponding weights, and then the resulting product is going to convey to the subsequent node, and all the inputs directed to a certain subsequent node are combined through addition. Now there are three types of layers in neural network representations. The first one is an input layer, and the other an output layer, and the other is called the hidden layer. Now the input layer is the layer where the input data is going to fed, in which the network will going to process, and the output layer is the layer that returns the output of the model. And in the middle of the two, that is in the input and the output layers, we can have one or more layers, and these layers are called hidden layers. So for example, here we have an input layer and an output layer. The first layer is an input layer, and the last most layer is an output layer, and anything in between that is called hidden layer. And specifically here, for example, the input layer has 3 nodes or 3 inputs, and the output node has only 1 node. And in the middle we have 3 hidden layers. The first hidden layer has 4 nodes, again the second hidden layer has 4 nodes, and the third hidden layer has also 4 nodes. Therefore, as long as we have more hidden layers, we call the neural network as deep neural network, or sometimes we call it as the method of learning is called as deep learning. So even if we have just a single hidden layer, we call that a deep neural network model. When we have 2 hidden layers, it is more deep. When we have 3 hidden layers, it's more deep. Therefore, the larger the number of hidden layers, the more the deeper of the neural network model, and we call in general as deep neural network. So here we have one input layer plus the first hidden layer. We have 2 layers. The second hidden layer, now we have 3 layers, and the third hidden layer, now we have 4 layers, and we have an output layer, we have 5 layers. And we call this model as a 4-layer neural network model, because we do not count the input layer as a layer. Therefore, 1, 2, 3, 4. This representation is a 4-layer neural network model. 4-layer neural network model. Now let's represent simply a simple linear regression model as a neural network model. Previously, we have seen how to represent the multiple linear regression model as a neural network model, but now let's specifically concentrate on a simple linear regression model, which is just a regression model having only one covariate. So for a simple linear regression model, we have a single covariate, and the representation will be something like this. We have a constant term for the intercept or for the bias term, and we have one covariate or input variable. So this representation is just simple linear regression model, or the model is y equals 1 times b plus x times w, or simply this model is nothing but y equals b plus w times x. So this is just a simple linear regression model. So we have 2 input nodes and we have 1 output node. Now let's represent this simple linear regression model as a deep neural network model. By default, this representation is a single layer neural network model. But if we have at least one hidden layer, we call that model or that specific neural network as deep neural network. So let's represent this single layer neural network model or simple linear regression model as a deep neural network model. So it could be something like this. We have an input layer similar to the first one. We have an output layer, again similar to the first representation of the single layer neural network model, but now we added one hidden layer having 3 nodes. So this simple linear regression model is represented as here a single hidden layer neural network model or a 2-layer neural network model. This is a single layer neural network model. This is a 2-layer neural network model or a single hidden layer neural network model. Now here we have to keep in mind that, for example, H1 is nothing but it is obtained as 1 times W01 plus X times W11. Similarly, H2 is nothing but 1 times W02 plus X times W12. And the same is true here, Y. Y equals 1 times W02 plus H1 times W12 plus H2 times W22. So this single layer neural network or simple linear regression is represented as simply a 2-layer neural network model. Therefore here Y is nothing but W02 or 1 times W02 plus H1 times W12 plus H2 times W22. And H1 is nothing but 1 times W01 plus X times W11. And H2 is nothing but 1 times W02 plus X times W12. Therefore, this can be written as in this form. Just H1, instead of H1, we substitute the value 1 times W01 plus X times W11. Similarly, for H2, we replaced it by 1 times W02 plus W12 times X. Now here we have X and we have all the other parameters. This can be rewritten as in this form. Just W02 plus W01 times W12 plus W11 times W12x plus W02 times W22 plus W12 times W22x. Now here we have the covariate x. Let's collect similar terms together. So here we have W02 plus W01 times W12 plus W02 times W22. And similarly we have plus W11 times W12x plus W12 times W22x. So collecting similar terms together, it becomes something like this. Now here W02 plus W01 times W12 plus W02 times W22 can be considered as the bias term or the intercept term, or that's of the constant term. And here W11 times W12 plus W12 times W22 can be considered as the coefficient for x or the weight for x, and let's call it as simply W. So this is nothing but now this two-layer neural network becomes B plus WX, which is just a simple linear regression model. So this single layer neural network model, or this simple linear regression model, and this two-layer neural network model are exactly the same. They are exactly the same. So from where, or what is the difference between neural networks and the usual standard models? So there is one important term missing in the current way of representing the neural network model. There is one important term missing, which is called nonlinearity. So in order to realize the potential power of multi-layer neural networks or deep neural networks, there is one more key ingredient, which is called activation function. So this activation function is a nonlinear function that is going to be applied to each hidden unit after that of the usual affine transformation. So an activation function is nothing but a certain nonlinear function that transforms the inputs into a certain nonlinear output or nonlinear result. So the common activation functions used in neural network models are the sigmoid activation function, the tanh activation function, or which is called hyperbolic tangent activation function, and the ReLU activation function, or rectified linear unit activation function. Now the sigmoid activation function is just the logistic function which transforms any input z into a value between 0 and 1 inclusive. So this just for any value of z, the output will be in between 0 and 1. And for that of a tanh activation function or hyperbolic tangent activation function, it squashes any inputs into the interval -1 and 1. So for any value of z, the output will be between -1 and 1 inclusive. And for that of a rectified linear unit activation function, it sets all the negative values into 0, and then it takes the maximum value of this, or it takes the maximum value of just the input z or 0. So if there is any negative value, then the value will be 0, otherwise the positive values are taken as they are. So it takes just the maximum value of 0 or z. That means all the negative values are going to be considered as 0. So these are some of the common activation functions which makes deep neural networks most powerful. Now let's consider applying a sigmoid activation function to the previous example that we have seen. Previously we have this model H1, here we have H2 in the input nodes. That's of in the hidden layer, sorry. So here we can pass H1 and H2 through a certain nonlinear activation function. Let's consider that just phi of h1, phi of h2. The constant term is left as it is. So the model will be phi of h1, phi of h2, and everything else is the same. So here in the hidden layer, and particularly in the hidden nodes, we apply that of a sigmoid activation function. Now this model can be written as y equals w02 plus phi of h1 times w12 plus phi of h2 times w22. But phi of h1, or specifically h1, is nothing but 1 times w01 plus x times w11, and h2 is nothing but 1 times w02 plus x times w12. So this can be written as in this form. Instead of h1, we write as w01 plus w11x, and instead of h2, w02 plus w12x. So these values should pass through that of a sigmoid activation function. Now for this particular example, phi is nothing but the sigmoid activation function. So this can be written in this form. Specifically, phi of w01 plus w11x is nothing but it's just 1 over 1 plus e to the power of minus w01 plus minus w11x. But this can be rewritten as e to the power of w01 plus w11x over 1 plus e to the power of w01 plus w11x. And the same is true for this term. And now clearly y is not a linear function of the covariates x. Therefore this model is no longer that of a linear model. Rather it is a nonlinear function of the covariates x. So in general, with activation functions, it is not possible to collapse the deep neural network model into a linear model. But unlike that of the standard linear models, here the parameters are not easily interpretable. So this is just the basic introduction to that of neural network models, or how the neural network models are different from that of the standard statistical linear models.